Okay, so in this video we want to discuss the ideas of domain and range of a relation or of a function. Relations all have domain and range. Okay, so as do functions being a subset of relations, they also have domain and range. In this video we want to talk about what domain and range is, and then we want to review the notation we use, so set notation, to describe domains and ranges, and then we'll also be having a look at implied domains. Okay, so in the previous section, we defined a relation as being a set of ordered pairs or coordinates. The other thing I should have said is that technically it's a set. So we need to actually use set notation when defining a relation. Often we don't, we shortcut, but technically it is a set of ordered pairs. It could be described as using a rule, or it could be literally a list of points. So as I said, the relation could be defined by a rule. For example, y equals x squared defines a relation. But if we're formally defining a relation, we must remember that it's a set. So it should be defined as a set. And so the relation whose ordered pairs are defined by the rule y equals x squared is technically defined in this notation. So these curly brackets, okay, these curly brackets define a set. The bit at the beginning here tells us, so the bit before the semicolon tells us what kind of things have we got in this set. So the curly brackets tell us we have a set of things, and they're all going to be ordered pairs. We have a set of ordered pairs. We have a set of ordered pairs such that, that's how we read the colon, y is equal to x squared. So we have a set of ordered pairs, x comma y, such that the y value of those ordered pairs is equal to the square of the x value. Okay? So that's the formal definition of the relation using set notation. The domain of a relation is the set of first elements in the ordered pairs of the relation. So that is, it's the set of all the x values in the relation. The range of a relation is the set of second elements in the ordered pairs of the relation. So that is the set of the y values. Again, we must realize that domain and range are sets, and so appropriate set notation must be used. Okay. So let's consider the following relations, and we want to state the domain and range of each, and in doing so we're going to review two different set notations. Okay, so the first relation here is a set of ordered pairs such that they all follow this rule. The y coordinates in the ordered pairs are all equal to -2 times the x coordinates plus 2. We can see from the graph here also that we don't have that complete relation. Okay, so it's actually been restricted. So we can see we've got a hollow circle here at -3, 8 and a closed circle here at 2, -2. So in terms of domain, domain is the set of x values. Okay, so our smallest x value is -3, but that's not included on the function. And our largest x value is +2, but that is included. So our domain is all of the x values that go from -3, not including -3, up to 2, including 2. So the domain, and we abbreviate domain and range just by using the first 3 letters of each word, dom and ran. Okay. If this was a function with a name, if this was called f of x, I would write domain of f. There's no other function or relation in this particular example, so I'm just going to talk about domain. So the domain is equal to, now there's two different ways we could write it. So the domain is equal to the set of x values, so it's the set of x values such that x is, -3 is less than x, which is less than or equal to +2. So we could write it that way, or I'm just going to move that over because I'm going to need a bit more room here. Or the other way to write that, because that's very cumbersome, if you want to use inequalities, you have to use the set notation. Okay, so it's not a nice way to talk about the domain. Much more preferable is to use what we call interval notation, which is a way of describing an interval of numbers, so from a value up to another value. So we're going from -3 up to 2. -3 is not included, so we write a round bracket around -3, and +2 is included, so we write a square bracket around +2. The second notation, the interval notation, is almost always my preference when talking about domain and range. If we want to describe the range of this relation, which is also a function, it would be the set of y values such that, so the smallest y value is -2, and that's included. So y is bigger than or equal to -2, but it is less than 8, which is the largest y value. Okay, so we either write it that way, or we just talk about the range as being equal to the set of values that go from -2, including -2, up to 8, not including 8. You don't need to write y anywhere in the range unless you're using the set notation. Okay. Similarly, you don't need to write x anywhere in the domain unless you're using that curly bracket set notation. That's purely just how you write that set notation. Curly bracket, what kind of things are in here? X values. What kind of things are in here? Y values. If you're just writing an interval, you don't need to write x or y. Domain, implicit in writing that the domain is equal to something, is domain we know is about x values. Okay, so the x values or the input values are a part of the set. The other thing to be aware of is notation. Domain is equal to a set. Domain represents a set of x values. So it's equal to that interval. However, if you wanted to say that x could be an element of the interval from -3 to 2, you would use that notation. X can be anything within that. So x can't equal that. X is not a set. X is a particular value. But the domain is a set of x values, so it can equal that set. Okay, B, we have a relation that is a set of ordered pairs defined by the rule y equals 3 minus x squared. And again, we can see from the graph that it's been restricted. So the domain is all about the x values. So the x values here, the smallest x value is -3, and that's an included value. And the biggest x value is +2, and that's not an included value. Okay, so in this case, our domain is going to be the set of x values where x is bigger than or equal to -3, but less than 1. Sorry, it's not, sorry, I said 2 before. The x value there is 1, but less than 1. Or as an interval, we can just write that as -3 with a square bracket to indicate that -3 is included, up to 1 with a round bracket. Careful that your round brackets don't look vaguely square, with a round bracket to indicate that 1 is not included in the set. Okay. The range in this case, be a bit careful here because sometimes people get bamboozled by the endpoints. The smallest y value corresponds to this endpoint here. It's there, and that's an included point. The biggest y value is not at this end point. The graph gets higher than that. The biggest y value is at the turning point, and that's also an included point. So the range is everything from -6, so it's a set of y values from -6, including -6, up to, we can see from the rule that that turning point is going to be at 3, up to and including 3. Okay. Or as an interval square bracket -6 up to +3 with a square bracket. Okay. Alright, part C, some sort of function with an asymptote. So in terms of domain, the smallest x value here is at -3, and that's included. And then the graph continues on and on. There's nothing to indicate that it's stopping. There's no endpoint. Okay, unless there's a hollow or closed endpoint specifically, that you assume the graph continues. That's important for you drawing a graph too. When you draw a graph, it shouldn't just stop randomly in the middle of the axes here. If it's stopping, it's either an included point or not an included point, or it shouldn't be stopping there at all, and it should be extending right out to the edge of your axes to indicate that it keeps going. Okay. Alright, so it's going to keep going, the domain keeps going forever from there. So the domain is the set of x values such that x is bigger than or equal to -3. Or we could write that as an interval. In the smallest value is -3, and that's included. And we go on forever, we go up to infinity. And you should always have a round bracket around infinity, because infinity can't actually be reached. It's not a number, it's an idea of something very, very big. So you can't ever include infinity in the set, given that it doesn't actually exist. It's an idea of bigness. The range of this function, okay, so let's think about our y values. The smallest y value is happening at this point, -4, and that's an included point. And then we go up until the graph is getting closer and closer and closer to +4, so it can include everything up to +4. We've got an asymptote at +4, so it can't actually reach +4. So our range is going to be the set of y values such that -4 is less than or equal to y, which is less than +4. Or as an interval, which would be my preference absolutely, from -4 inclusive up to +4 not inclusive. Alright, and then we have a log graph here. We'll review some of these other functions, exponentials and logs, further down the track, but they should be familiar things to you. So the log graph has an asymptote at the y-axis, otherwise it continues on forever. So if we're talking about x values for which this graph exists, okay, it's getting more and more flat, but it still continues on and on and on forever. So it's going to get bigger and bigger and bigger endlessly. Similarly, it's getting closer and closer and closer to the y-axis, but it still continues on and on forever, just getting more and more minusculely close to the y-axis, if that's an accurate phrase, which I don't think it is. So the domain, the graph exists for all y values. Sorry, I was talking about range there, wasn't I? So the graph exists for all y values. It doesn't exist for all x values. It doesn't exist back here, and it also doesn't exist at the y-axis because the y-axis is an asymptote. So it doesn't exist here, but it exists for every value bigger than 0, and then it keeps going on forever that way. Whereas for the range, it exists everywhere. Okay. So the domain here is going to be the set of x values such that x is bigger than 0, or I'm going to write this in 3 different ways. Or it's going to be the interval from 0, not including 0, up to infinity, obviously not including infinity. But we also have a special notation for this, and we can write r plus, which is positive real numbers. Okay. So particularly given that 0 is not included here, 0 is not included in the positive real numbers being any number that you can represent on a number line. Okay. So the domain in this instance is the positive real numbers. Now, the range, okay, we could technically write it a few ways, but we would actually always choose only one way to write this. We could say it's the set of y values where y is between -infinity and positive infinity. We could say that it's the interval from -infinity up to positive infinity. But actually, in practice, we wouldn't ever write either of those things. All those things are just r, all real numbers. So please don't write the interval from -infinity to infinity. If x exists or y exists from -infinity to infinity, then it is an element of r. It's an element of the real numbers, so we would use r. Alright, a couple more examples over the page. So e, we've got some sort of hyperbola here. It's been translated to the right by 2. So it has an asymptote when x equals 2. So in terms of domain, it exists everywhere except at 2. Okay. So we could write this a few ways again. Technically we could say the domain is the set of x values such that x is less than 0 or, so union, x is bigger than 0. Okay. It's not and, because the and is the intersection. It's all the x values that fit both that, and there are no x values in both that and that. So you would be saying the domain is nothing. So it's the union, or, which could also be written as the intervals from -infinity up to 0, not include, sorry, not 0. Sorry, it's not 0, that's not included, it's 2, that's not included. Up to 2, union from 2 up to infinity. But again, I wouldn't write any of those things because it's much easier to say the domain is all of the real numbers except for excluding 2. Now, if you want to exclude a single value or a list of values from the real numbers, they must be in set notation. They must be in the curly brackets because R is a set you can't subtract a number from a set, you have to subtract a set from a set, okay? Exclude a set from a set. So the domain of the hyperbola is all the real numbers except for 2. If we're talking about the range, the hyperbola exists everywhere except at 0. So for every y value bigger than 0, there will be a point on the graph somewhere way out here, or somewhere up here. For every y value less than 0, there'll be a point on the graph, but when y equals 0, there's an asymptote. So similar notations here then. Our range, we could, if we really wanted to, say that y, we have a set of y values where y is less than 0 or y is bigger than 0, which would be the same as saying, sorry, let me try that bracket again. Same as saying we can go an interval from negative infinity up to 0, not including 0, union an interval from 0 up to infinity. But actually the quickest way of saying that is that we have all the real numbers except for 0. Okay, so these would definitely be our preferences here. Okay, and then F, we have a square root graph that has been reflected in the y-axis. Okay, so it is going this way instead of this way. So let's think about the domain here. The largest x value is at 0, it doesn't go past there, and that's an included point, and we can include every x value before that. So the domain here is going to be, sorry, let's start with the set, which is not at all my preference, the set of x values where x is less than or equal to 0. We could also say the interval, where we go from negative infinity up to 0, including 0. Or we can talk about r minus the negative real numbers, but the problem is that the negative real numbers don't include 0, so we would need to add that together with, so it needs to be in the union with 0. So r minus union 0. Personally, my preference here would be this one. Okay, it's generally neater. R minus on its own is nice, but R minus, the minute you've got to have R minus union 0, it's not much fun. Okay, range is going to be similar. The smallest y value is at 0, and then the graph keeps getting bigger. Okay, it's getting bigger at a slower and slower rate, but it is going to keep getting bigger and bigger indefinitely. So our range is either the set of y values where y is bigger than or equal to 0, or it is the interval from 0 including 0 up to infinity, or it is r plus positive real numbers along with 0, union 0. Again, if you want to add r minus or r plus to something, it has to be added to a set, okay? You can't have the union of a set and a number, you have to have the union of two sets. Okay, 2 more examples. Part G, we have a piecewise function. We'll talk more about these in a subsequent video. But it is essentially a function that is defined by 2 different rules over different parts of the domain. The fact that we've got the graph helps us here. So the domain of this function, if we think about it, it's tempting to think, oh, it's broken here, so there's something happening at 0. But actually, the graph exists here on this part of the graph at 0. So it exists at 0. It exists for all the positive values on that branch. It exists for all the negative values in this branch. So actually the domain is all the real numbers, which would be my preference. Technically we could say it's all the x values where x is somewhere, sorry, it can't be including 0, infinity, is bigger than negative infinity and smaller than infinity, which is the same as saying it is the interval from negative infinity up to positive infinity, but we don't write any of those things. If we can write those things, we just write R. The domain is R. And the range, okay, so in this instance, the range, the graph has a break in the middle. So it goes from negative infinity all the way up to negative 1, including negative 1, but then it doesn't, there's no y values between negative 1 and positive 1. Doesn't include positive 1, and then it's everything above there. Okay, so we are talking about the set of y values such that y is less than or equal to -1, or, so union, y is bigger than +1. We can write that using intervals as going from -infinity up to -1. Now which one was it? So included -1. Union from +1, but doesn't include +1, up to infinity. Now, we could also write this as all the real numbers except for, but you have to be careful here, and I guarantee a lot of you would make mistakes, and for that reason, this is my preference here. It's easier to talk about what you do have rather than to talk about what you don't have. So if we think about this, if we want to think about we've got all the real numbers except for a set of numbers in the middle here, we want to exclude 1 from all the real numbers, but we don't want to exclude -1 from all the real numbers because it still needs to be there. So this is the set of values that need to be excluded. We need to exclude, we don't want to exclude -1 because it needs to remain in the real numbers, but we do want to exclude +1. Okay, so this is a set. We're excluding a set from a set. Okay. So that's different from if you did all the real numbers excluding with curly brackets -1 to 1. You're not, sorry, you shouldn't have said to 1. When it's curly brackets, that's a list of numbers. It's not everything in between -1 and +1. It is just the numbers -1 and +1. So that would be everything from -infinity except for -1, except for +1, and include everything in between, which is not what we want. Okay, so you need to be careful about, you need to be clear on the differences in those understandings. This is hard, working out what to exclude when you're excluding a set of values from the real numbers, and you tend to get the brackets around the wrong way. So in this instance, I think it's easier to talk about what you do have. I have everything from -infinity, which is this line. I have everything from -infinity up to -1, inclusive of -1, along with everything from 1 not including 1 up to infinity. Okay, this one's a bit tricky because I haven't actually given you enough information to answer this question. We won't talk about the range here because we actually don't know what the range is. It's slightly complicated. I'm not worried about the notation here, but I do want to use this as an example to talk about how we could talk about this domain. And again, it's not clear here that whether or not we go on forever. Let's assume it does. So if we wanted to talk about the domain here, the domain is just when x equals 0, when x equals 1, when x equals 2, 3, 4, 5, 6, 7, -1, -2, etc. So it's just the positive and negative whole numbers, including 0. They are integers. The domain is the set of integers. And we have a special notation for integers, which is z. If we just wanted to talk about positive integers, it would be z plus, but this also exists for negative integers. If we wanted to talk about just negative integers, it would be z minus, bearing in mind that z plus and z minus, neither of those include 0, so you would need to put the union with 0 if that was meant to be included. The range here is quite complicated because it's square numbers. I'm not going to worry about that. I'm not really interested in that notation. I just wanted this as an example to talk about the notation for integers. Okay. So just, I've used those examples to revise a lot of that set notation which you should have met before in Year 11. Just some summary notes though, just to remind you of the things that are important. So unless using interval notation, that is square or round brackets indicating a range of values, curly brackets must be used to indicate a set. So you can't just talk about x bigger than 3. Okay, that's not a set. So you can't say that domain equals x bigger than 3. This notation doesn't make any sense. It would have to be equals a set of x values such that x is bigger than 3. Okay. So correct notation when talking about domains and ranges, intervals is generally easier. When using interval notation, square brackets indicate included endpoints, round brackets included not included endpoints. So we've revised that. There's an example there. When using infinity in interval notation, it should always be surrounded by a round bracket, since infinity itself can never be included in the set. R represents the set of all real numbers and should always be used in place of the interval -infinity to infinity. Sorry, that's awkward on separate lines. Let me just write that on the one line. It should always be used in place of writing -infinity to infinity. If you're ever tempted to write that, it should be R. Okay. R plus represents the set of all positive real numbers and therefore doesn't include 0. 0 isn't a positive number. Similarly, R minus represents the set of all negative real numbers and doesn't include 0. So R plus is 0 to infinity, not including 0. R minus is negative infinity to 0, not including 0. So it's important to understand that R minus union R plus does not equal R, because it doesn't have 0. Okay, it equals R excluding 0. Alright, so just be careful about that. 0 to infinity with a square bracket can be represented using R plus, but it would have to be R plus union 0, making sure that the 0 is in a set, because you need to add together two sets. Similarly, negative infinity to 0 including 0 can be represented as R minus union 0. The backslash is used to exclude elements from a set. So for example, R excluding 0 is a set of all the real numbers except for 0. This notation is common when functions have asymptotes. So hyperbolas in particular, truncuses, the domain would be R excluding a value. Note that when adding to a set using the union or subtracting from a set using the set difference, that is the backslash, you must remember that you can only add sets or subtract sets, so the elements being added or subtracted must be in curly brackets or given as an interval. So you can't just have R excluding 2, it has to be including the set of values that include 2. Okay? If you want to exclude two different values from R, you would have curly brackets, R excluding 2 and 3. Okay, that's just excluding those two separate numbers. If you want to exclude all the numbers between 2 and 3 inclusive, then you would have an interval. And that means you would be left with, if you've excluded 2, you wouldn't have 2 left in your real number set, and you also wouldn't have 3 if you've excluded 3. So if you want 2 and 3 to remain in the set, then you don't exclude them. Z represents the set of all integers, positive and negative whole numbers and 0, and the notations Z plus and Z minus can be used to represent positive and negative integers respectively. Note that neither Z plus nor Z minus include 0, so once again, Z minus union Z plus does not equal Z. Okay, so just be careful of that. Alright, so just some reminders. So let's represent each of the following sets using interval notation. So if we have the set of x values where x is bigger than 5, that means that x can be an element of the set of the interval that goes from 5, not including 5, up to infinity. If we have the set of x values such that x is between negative 2 and 15, including negative 2 and not including 15, that means that x is an element of the interval from negative 2, including negative 2, up to 15, not including 15. If we have the set of x values where x is less than or equal to negative 8, then that means that x can be an element of the interval from negative infinity. The smallest element in that interval is well, there isn't an element, it's negative infinity, up to negative 8 and includes negative 8. The set of x values such that x is less than negative 5 or x is bigger than 5 as an interval would be x is an element of the interval from negative infinity up to negative 5, not including negative 5, union from 5, not including 5, up to infinity. Alright, as an interval, R plus, now it doesn't say x is an element of, so I'm not going to write x, whereas these were x is part of, this set is about x values, so hence why I included the x is an element of here. R plus is equal to 0 to infinity, not including 0. R excluding 0 as an interval is equal to negative infinity up to 0, not including 0, union from 0 up to infinity. So it's everything from negative infinity up to infinity except for the 0. So it's really just 0 that's been excluded in the middle there. Alright, this last one, R minus excluding negative 2. Okay, so that's going to be equal to everything from negative infinity up to negative 2 but not negative 2, union from negative 2 up to, now it's just R minus, so up to 0 but not including 0. Alright, then we might have relations with restricted domains. So sketch a graph of this relation. So it's a set of x and y values such that y is equal to x squared plus 5x and x is an element of -5 to 3, including -5, not including 3. Sketch the graph and state the range. Okay, so the rule and the domain are what's important here. Okay, so the rule is a parabola. Y equals x squared plus 5x. It's a happy parabola, so this shape. If we factorize it, x plus 5, we can see easily that we're going to have x-intercepts at 0 and 5. So you really should be able to sketch this parabola, x equals 5, without having to write any of this down. You really should be able to maybe just the factorized and then be able to see where your x-intercepts are. We are going to need to think about the turning point, but let's have a think about what we've got so far. So we've got a happy parabola with x-intercepts at 0 and 5. I'm just drawing a rough sketch. I'm not going to draw it in properly yet. 0 to 5, and it's going to go this way. So we want to think about where the turning point is. And then we also need to think about the domain. So actually, we're not going all the way up to 5. Okay, we're not going to here at all. We're going to be stopping at 3, which will be before we get to that second x-intercept. Let's calculate the turning point. So the turning point is going to be halfway between those x-intercepts, which will be when x equals 5 on 2, or 2.5, which means that y is going to be at 5 on 2 squared plus 5 times 5 on 2. So I'm just substituting the x value into the rule to work out what y value corresponds to that. So that is 25 on 4 plus 25 on 2, which is 50 on 4. So 25 on 4 plus 50 on 4. Sorry, I was just thinking we shouldn't have a positive y coordinate here, and I realised my error. My apologies. When we solve this, we don't get x equals 5, we get x equals -5, which means that the turning point's at -5 on 2. -5 on 2 all squared is still positive 25 on 4, but we'll be subtracting 25 on 2. So 25 on 4 minus 50 on 4 is -25 on 4. So my turning point is at -5 on 2, -25 on 4. We would absolutely need to calculate that. X-intercept's turning point. Y-intercept is also going to be at 0. If 0 is an x-intercept, that'll be the y-intercept. Let's think about these endpoints. So when x equals -5, endpoints. So and that's basically looking at that domain. When x equals -5, y is going to be -5 squared plus 5 times -5. So that is 25 minus 25, which is at 0. So that's one of the x-intercepts. Sorry, again, I stuffed up my sketch before. So it's going to be doing this, but where the domain only goes from -5. So we're going to start at that turning point, and then we're going to go up to 3. So we've got not start at the turning point, start at the x-intercept, and then we need to work out when x equals 3, what does y equal? Let's calculate all those things before we draw the graph though, so we can get some sense of scale. So I actually didn't need to calculate that if I'd correctly thought about this already. When x equals 3, y is 3 squared plus 5 times 3, so that's 9 plus 15, which is 24. Okay, so I need to think about, I'm going to have 1, 2, 3, 4, 5, 1, 2, 3. Okay, x-intercept there, and that's an endpoint and it's included, so square bracket at the -5. X-intercept at the origin, turning point at -2.5, -25 on 4, which isn't very big compared to the fact that we need to go to 324 up here. Okay, so I'm just going to try and draw in the shape and sort of stop somewhere up here roughly in line with that 3. So that is the point 324. It's a not included endpoint, must be clearly a hollow circle, and we label with coordinates at the point. Always label with coordinates, label at the point rather than marking 24 and 3 here. It's less ambiguous. The turning point is at -5 on 2, -25 on 4. X-intercept at 0, 0. We don't technically need to label 0, 0. and negative 5, 0 we do need to label. You can label that if you want, but the origin is the one point that if the origin is a key feature, we understand the coordinates of the origin to be 0, 0 without you labeling them. Okay, so there's our graph. So the question was to sketch the graph, which we've done. So we've got the rule with the domain, so it's got a restricted domain, hence we're going to have included and not included endpoints. We also want to state the range, okay? So the range of this graph, the lowest y value is at the turning point, negative 25 on 4, and that's included. And in this instance, the biggest y value is at the endpoint where x equals 3, and that's 24, but that's not an included endpoint, so that value of 24 is not included in the range. Okay, some instructions there about how to restrict the domain of a function with your CAS, and that's using the given that symbol. I actually strongly discourage you from if you're defining a function with your CAS, I would never restrict the domain when I define the function. I find that it can create problems when you do certain calculations with the functions. You're best to define the function without the domain restriction, and either include it later if you're trying to solve things, or just know it. If you solve it equal to something and you get 5 solutions but only 2 of them were within the domain, then you just write down the 2 relevant solutions and you ignore the others. Similarly, you can also use the given that symbol to restrict the domain in the graphing screen. However, again, I wouldn't advocate it. It generally makes things more cumbersome. I would just draw the whole graph and understand that I want to stop the graph at when x equals 2 and use my calculator screen to work out what the coordinates of that endpoint are. So some instructions there for you to have a look at. I'm not going to go through that, A, because this video is getting quite long already, and B, because I would use the given that when I want to restrict the domain when I'm solving a function. We'll talk about that in specific cases where that comes up, particularly in the circular functions. But I would never define a function with a restricted domain in my CAS, and I would never sketch a graph with a restricted domain in my CAS. I would just sketch the full function, define the full function, and just simply interpret based on the domain. Last thing we want to talk about in this video is the idea of an implied or a maximal domain. So if the rule of a relation is given with no specific domain, then its domain is assumed to be the largest possible set of x values for which that relation exists. And that's called the implied or maximal domain of that function. All polynomial functions, linear, quadratic, cubic, quartic, etc., have an implied domain of R. Easy. Since there's no values of x for which these functions don't exist. Of the relations that we're familiar with so far, there are 2 main kinds of relations, or 2 main algebraic features in those relations that mean that they have implied domains that are not R. And the first is any relation that involves a square root, or in fact any even root, 4th root, 6th root, 8th root. And that's because it's impossible to take the square root or any even root of a negative value. And therefore that has implications for the domain of that function. So let's consider each of the following relations and state the implied domain. So y equals the square root of x. So we know that whatever's under the square root has to be bigger than or equal to 0. Okay, so we know that that thing, x, has to be bigger than or equal to 0, which means that the domain here is going to be everything from 0 to infinity. Same implies here. No matter where the square root is in your function, whatever's underneath it has to be bigger than or equal to 0. So x plus 3 has to be bigger than or equal to 0, which means x has to be bigger than or equal to negative 3. So the domain, sorry I missed the bracket there, the domain for this one is going to be from negative 3 up to infinity. That will ensure that we're always taking the square root of a positive value. Similarly for this one, square root of 6 minus x, that thing under there, 6 minus x, must be bigger than or equal to 0 so that you can take the square root, which means that negative x is bigger than or equal to negative 6. I've subtracted 6 from both sides, and now I'm going to multiply both sides by negative 1, which means reversing the inequality. So x is less than or equal to 6. Domain is equal to negative infinity to 6. This can be a helpful tool when sketching these graphs to think about the domain first, because the transformations in this one are a bit tricky. We'll talk more about transformations in an upcoming topic. But there's a reflection in the y-axis and a translation left or right by 6, depending on which order you do those transformations in. And that can be quite hard for many students to identify accurately. So if you think about the domain first, the fact that the domain goes from negative infinity to 6, I know there's a reflection of the y-axis, so the shape is like that, but if the domain is from 6 and below, that means that it must look like this. Okay, so it helps you to think through those transformations as well. Again, we've got a square root here. We've got square root of x squared minus 4. So we know that x squared minus 4 must be bigger than or equal to 0. Sorry, x squared minus 4 must be bigger than or equal to 0 in order for that us to be taking the square root of a positive value. Now that's a quadratic inequality. Solving a quadratic inequality, you must consider a graph. X squared minus 4 is a parabola translated down by 4. Has x-intercepts at plus minus 2. It is bigger than or equal to 0 if x is bigger than or equal to 2, or if x is less than or equal to negative 2. That's where x squared minus 4 will be bigger than or equal to 0. So when x is less than or equal to negative 2, or when x is bigger than or equal to positive 2. So as an interval, we would write our domain goes from negative infinity up to negative 2, including negative 2, union from positive 2 up to infinity. If x is any of those values, x squared minus 4 will be a positive value, and therefore we can take the square root of that, and hence the function will be defined. So relations involving square roots are going to have implied domains that aren't R. Similarly, relations involving fractions are going to have implied domains that aren't R, and that's because we can't divide by 0. Algebraically, we can't divide by 0, so therefore anytime we've got a fraction, we need to think about what value would make the denominator equal to 0, and therefore we must exclude that from the domain. So simplest example of this, y equals 1 over x. We know that the denominator of the fraction cannot equal 0, so in this case x can't equal 0, and so that means that the domain could be any real number except for 0. Similarly here, the denominator can't be 0, so 2x minus 7 cannot equal 0, which means 2x cannot equal 7, and x cannot equal 7 on 2. So therefore the domain is going to be any real number except for 7 over 2. In the third example here, we know that the denominator can't be 0. So x plus 1 times x minus 5 cannot equal 0, which means that x cannot equal negative 1 and x cannot equal positive 5. So our domain is going to be all the real numbers except for 2 individual values. So a list of values in curly brackets, negative 1 or 5. Now, these you might be able to think through what they look like to think about the domain. This is not a function we're familiar with, and we can't think through that graph to be able to determine the domain. So we have to be able to think algebraically about what domain means and which x values might this function not exist for. Let's just have a quick look at what that graph does look like to verify what we've just found there. So if I sketch the graph of 1 over x plus 1 times x minus 5, we get this graph here, and it does indeed look as though it's got asymptotes at x equals negative 1 and x equals 5. We can there's no function in your CAS to find the equations of asymptotes, but you can sort of test for it by having a look in trace mode. So if we go to menu, analyze graph, which is, no, sorry, not analyze graph, 5, which is trace, and 1 for graph trace, that puts a cursor on the graph. You can scroll around the graph, the coordinates of the point are sitting down here in the bottom right of screen. You can also jump to any point on the graph. So if I want to go to the point where x equals 3, when I'm in trace mode, if I just type the number 3, just somewhere on the screen, x equals 3 will appear, and if you press enter, the cursor will jump to the point on the graph with the next coordinate of 3, and you'll see the coordinates at the bottom right there. So if I want to jump to negative 1, when x equals negative 1, which I think is an asymptote, so if I just type negative 1 and press enter, the cursor will jump to the point on the graph where x equals negative 1. And what it's confirming for me, in me asking it to do that, is that actually when x equals negative 1, the graph's undefined. So there is indeed, the function's undefined, so there is indeed an asymptote there. Similarly, I could type 5 and press enter. Oh, sorry, I typed 55. I've got to go back, sorry. Menu 4.5, back to Zoom Standard. Sketch the graph again because I deleted it when I undid it. My apologies. 1 over x plus 1 times x minus 5. Let's try that again. Brackets x minus 5. Alright, and again if I go into trace mode, menu 5.1, and I just type 5 and press enter, it does indeed tell me that the function is undefined when x equals 5. So therefore it makes sense that that value is excluded from my domain. Okay, let's get out of there. Let's have a look at this fourth example here. So again, we've got a fraction. This time there's not 1 on the numerator. We have 1 on the numerator of all the others, but it doesn't matter what's on the numerator. X could equal anything and the numerator would still be fine. The issue with the fraction is still solely to do with the denominator. Okay, so we know that x plus 4 cannot equal 0 if that expression is to be defined. So x cannot equal negative 4, which means the domain here is all real numbers except for negative 4. Okay, and then finally, I know this has been a long one, we want to have a look at, sometimes we might have combinations of even roots, so square roots or fourth roots or sixth roots, and fractions. So we need to consider both of those restrictions. So this first example here, where we have 1 over the square root of 5x minus x squared, we know that that whole denominator can't equal 0. So we know that the square root of 5x minus x squared cannot be equal to 0. Okay. We also know from the square root that 5x minus x squared has to be bigger than or equal to 0. So both of those things have to be true. Now, if 5x minus x squared were to equal 0, the square root of 0 is 0, and that would make the fraction problematic. So in this instance, we just need 5x minus x squared to be just bigger than 0. Okay. So that means that 5x minus x squared has to be bigger than 0. Bigger than 0 will mean we can take the square root, but it also means that we won't get 0 on the denominator, and therefore we can still have the fraction. So we want to solve that. Now again, we have a quadratic inequality, which means considering a graph, take out x as your common factor. Okay, just to, sorry, not to solve it, but to be able to help me sketch it. So it's a sad parabola with x-intercepts at 0 and 5. So it looks something like this. We want to know where that parabola is bigger than 0. It's equal to 0 at those x-intercepts, but it is bigger than 0 between those two x-intercepts. So that is when x is between 0 and 5. So the domain here is going to be the interval from 0 to 5, excluding both 0 and 5. If x were to equal 0, 5x minus x squared would equal 0, square root of 0 is 0, and we'd have 1 over 0, which wouldn't work. If x were to equal 5, we'd have the same problem. If x was anything bigger than 5, this would be a negative number and we couldn't take the square root of it. So only defined for those particular values. And again, this is a function that you don't know what it looks like. Okay, so if we have a quick look at what that looks like, control divide, 1 over square root of 5x minus x squared, it looks like that. And indeed, it does look like it exists just between 0 and 5. Again, you can have a look at graph trace. You can see when x is automatically gone to the point where x equals 0, which is undefined. The function's undefined when x equals 0. If I type 5 and press enter, the function's also undefined at 5. Obviously, for anything bigger than that, it's also undefined, but for anything in between that, it is in fact defined. Okay. All right, let's have a think about this last one. Okay, so we've got the square root of x plus 3 over 2x minus 5. Alright, so we need the denominator can't be 0. So we know that 2x minus 5 cannot equal 0. That's the first thing. We also need the whole fraction to be bigger than or equal to 0. Okay, so we need x plus 3 over 2x minus 5 to be bigger than or equal to 0. Okay, so that fraction will be positive if both the numerator and the denominator are positive. The numerator can be 0 because that would make it equal 0. So this will happen if x plus 3 is bigger than or equal to 0 and 2x minus 5 is bigger than 0. Can't be equal to 0 because of the fraction restriction. So that means if x is bigger than or equal to negative 3 and, so intersection, if 2x is bigger than 5, if x is bigger than 5 on 2. So we need the intersection of those two values. So if we think about that, here's 0, here's 5 on 2, here's negative 3. If x can be bigger than or equal to negative 3, but it also has to be bigger than 5 on 2, the intersection of those two things is just bigger than 5 on 2. And apologies if you can hear a noise in the background. My washing machine is going nuts. So the intersection of those things is x has to be bigger than 5 on 2. The other way that the fraction could be bigger than or equal to 0 is if both the numerator and denominator are negative. Now, if the numerator can equal 0, that's fine, that would make it equal 0. So if the numerator is less than, or if the numerator is less than or equal to 0, and if the denominator is also less than 0, then a negative divided by a negative is still a positive, and the fraction will still be positive. So that means x less than or equal to negative 3 and intersection 2x less than 5, so x less than 5 on 2. So again, thinking about the intersection of those two things, if this is 0, here's 5 on 2, here's negative 3, x can be less than or equal to negative 3 and less than 5 on 2. So the intersection of those two things is less than or equal to negative 3, the overlap. So those two things together say x can be less than or equal to negative 3. So we've got this, sorry, not intersection, or this. Okay. So that means that our domain is from negative infinity up to and including negative 3. It can include negative 3 because that just makes the numerator 0, which is fine. You can take the square root of 0. Union from 5 on 2 but not including 5 on 2 because 5 on 2 would be the value that would make the denominator 0, up to infinity, not including infinity. Okay, so that's quite a complicated example, but trying to think through what's happening. Alright, the work today on domain and range is a mixture of work from exercises 1A, 1B and 1C. So revising the set notation, understanding about domain and range, successfully describing domain and range, sketching graphs with restricted domains and ranges, thinking through implied domains and ranges.